All right, so this video is talking about Fourier synthesis, which relates essentially to Fourier transforms. And I just misspoke. It's Fourier. So that's how you say it. Fourier synthesis and Fourier transform. All right. Anyways, this is an extremely important topic. And so even though it's not often on a test, you really should know this if you're going to go anywhere in science and engineering. It's ubiquitous. So you could take some complicated waveform, maybe something that looks like this, and reduce it to a sum of sinusoidal waves. That's a big deal. Now, let's keep things simple for a minute. Let's start assuming we're just taking a snapshot of a wave at t equals 0, then it's going to be just some function of x. And let's pretend this is our function. Now, what you can do is this function doesn't look periodic at all. It just looks like a mess, but you could we could just say it starts at 0 and runs to L, and we could pretend the function is periodic over L, and just imagine there's an infinite number of copies this way and that. And we could do this Fourier series and analyze just one period of it and learn everything we needed to about the original signal. Whoa, this looks pretty complicated. Essentially, what you're doing is you're splitting this up into the average value, that's this term right here, and then you're going to add in a symmetric part with all the cosine functions, because cosine functions are symmetric. And then you've got an anti-symmetric part, which is the sine waves, because sine waves are anti-symmetric. So you can imagine if this was literally copied on both sides, some of it would be symmetric, some of it would be anti-symmetric, and that's what this is talking about here. Now, I'll mention you can see pages 40 and 41 for an example of this in volume 3. But for now, I'm going to go to a screen share. Give me just a sec. And I'll put a link to this simulation I'm going to show you here. It's a really good one. Let's go there. All right. And so you could see what we could do is we can adjust these coefficients A1, A2, A3. That was like the coefficients we saw on my board. I think I used lowercase a or something like that. And maybe they've switched sines and cosines, so maybe we could do that really quick. All right, so we've got a cosine function for our ANs. And then you could try just bundling different amounts of the different waves. And you could make different shapes out of this. And so notice if we look here at the bottom of the screen, this is the sum of all those different waveforms. And you could try adjusting them and make different shapes if you wanted to. And right here, we see all the different components added together there. And so you can see the sum of all of the waves in the middle produces the wave at the bottom. You might be saying, well, what if this is moving, or what different shapes can I make? Let me clear out my annotations really quick. Well, so first, let's look at what happens if this is moving, right? So this is why I was just restricting myself to one snapshot in time. You could always just move this thing using the wave velocity if you had to, right or left. So that's what happens if we restrict ourselves to just space first. You could do the same thing in time. And so oftentimes what we'll do is if we're doing a function with space, doing the transform gives us these coefficients at the top. This is called k-space sometimes. Or sometimes it's called reciprocal space. So if you're using x as your variable and you do the Fourier synthesis, you will you're sending the wave to k-space. Now think about this. If you specify 1, 2, 3, 4, 5, 6, well, I guess we got to get the zeros too, 11 numbers. 11 numbers characterizes this whole crazy shape here that's repeating over and over again. So think how much easier it would be to send data over the internet if you only have to send 11 numbers as opposed to this massive complicated waveform with a bunch of different data points spread out over time or over space. Okay, so that's the advantage of this. Or maybe if you want to do a high pass filter, you could just transform something into k-space and reduce all the high frequencies to 0 And then you've done, I guess that would be a low pass filter, right? You've cut the high frequencies and allowed the low ones to survive. There's all kinds of cool tricks you can use this. We're not going to put this on the test, but you should be aware of this one. So let me do a couple other things really quick. Let's clear all my drawings. All right, so annotate. Okay, there we go. So again, if we're in X space, doing the Fourier transform sends you over to the K space or to the reciprocal space. If you're in time, then doing the Fourier transform takes you from the time domain to the frequency domain. All right. And so there's different symbols for this. It's described on 40 and 41. If you have a pulse traveling, it looks like that. Let's take a look at some cool ones, though. You can see you can make a very triangular wave out of this. You can get a sawtooth. Oh, okay. Whoops. Thank you. So you could get a raunchy synth tone that way. This one's kind of interesting. This one is a little bit of foreshadowing. You could imagine a photon traveling through space or an electron traveling through space, and you model it as a wave packet. Maybe there's a bunch of different wavelengths centered around centered around this central frequency, whatever 6 is. So yeah, I guess you could have an interesting pulse shape come out of this one. Ooh. Anything else there? Oh, let's just call that go square. Looks pretty good too. All right. So if you want to learn more about that, do the problems in the book or come ask me in office hours. There's plenty of other information out there. I guess I'll maybe make one last comment here. I chose to go from 0 to L. If you're reading the internet out there, you're going to see people mix this up. Sometimes people will go from negative L over 2 to positive L over 2, or you could even imagine someone going from negative L to L, and that might change some of these numbers in here a little bit. So just be aware of that.